I'd like to now do an example on finding required force. In this particular example, I'm going to encourage you not to look at the examples that they show you online or in the book. I work this problem totally different than the way that they're working in the book. I'm using a trig approach for this problem. Okay, this example says a car weighing 5,700 pounds is parked on a 9-degree incline. Find the force required to keep the car from rolling down the hill. And then an additional question is, what is the force perpendicular to the hill? First thing we want to do is draw a picture representing this situation. I'm going to draw a horizontal line, and then I'm going to draw another line indicating the incline. Okay, that will be a 9-degree incline there. Sorry, let me kind of start over here. Okay, so there's my horizontal, and then here is my 9-degree incline. Okay, at some point, I have my car, and what I'm going to do is we are given, or we're asked to find the force that it takes to keep this car on the hill. So I'm going to say from here, there's going to be a particular vector we're going to call F, and that particular vector is representing the force that we need to keep this car from sliding back down the hill. Okay, from here, I'm going to drop a line straight down from that point down. Okay, that particular line is going to be represented using a vector that has a magnitude of 5,700. In other words, gravity is going to take effect. This car weighs 5,700 pounds, and so a vector straight down is going to represent that weight. Okay. From here, what I will do is a couple of things here. We see here that this is a 90-degree triangle because of the way I've drawn this straight line down for the gravity. In here are a couple of other things. They're asking, one of the parts of the questions is asking for the force that's perpendicular to the hill. So I'm going to draw another line that's perpendicular to the hill, so it's going to form a right angle with the hill there. Okay, and what's going to happen here is, and this is a little bit distorted, but the force vector that I have up top can be copied down to the bottom. Okay, so there's a copy of that force in that particular triangle. What happens there, that force, because we had a right triangle created right here, okay, that same right angle shows up down below because I'm taking that force vector and I'm copying it down, so it's going to be at the same angle and it'll have basically the same length. I realize my picture is somewhat distorted here. Okay, now from here, I'm going to use this larger triangle that I have drawn down below in the red and the blue to solve my problem. Okay, before I can do that, I need some angles. I have my right angle and I have the 5,700, but I need some other angles in there. Okay, first thing, I'm going to tackle finding the angle A inside of here. Okay, I can find that angle because I know that there's a right triangle formed there. I can say that A would be found by using 180 minus the 9 degrees that I was given, and then minus, I know that's a 90-degree angle, so A, that ends up being 81 degrees. And then what I want to do is I want to use that to find, let's call this a smaller angle, let's call that alpha. Alpha I can find by saying that I'm going to have 180 degrees formed by the incline here, okay, all the way up, and then to find that alpha inside, I can subtract the 90 degrees that I have here from 180 minus the angle A that I just found, which was 81, and then that would give me the alpha that I have on the inside. Okay, that ends up being 9 degrees. Is that a coincidence? In other words, that 9 degrees you see is the same 9 degrees that they gave me, and the answer is no, that's not a coincidence. Okay, so I know alpha inside is a 9-degree angle. What I'm going to do is I'm going to take this triangle that I have drawn, and I'm going to take it out, and I'm just going to kind of simplify my picture, because I don't need everything I have drawn up above now that I've created this triangle. Okay, in this triangle, you'll see that the 9-degree angles across from the 5700 and then the 9 degrees is across from the F. So I'm going to just take this and I'm going to rotate it around in a way that I can just kind of see it a little bit better. Okay, have the right angle. The short side over here was the force. I'm going to call this P for perpendicular, and then this is the 5700, and then this was 9 degrees. Okay. I need two things. I need to find F and I need to find P. To do this, I can use basically just right triangle trig. Okay, let's say first of all I want to find F. Okay, to do that I can use sine of 9 degrees. Okay, well, that's opposite over hypotenuse. The opposite side is F. The hypotenuse is 5700. Okay, doing that, if I solve for F, I get F is 5700 times sine of 9 degrees. Okay, plug that in your calculator using, make sure you use degree mode, and you get 891.6764507, and this would be pounds, because this is a force. Okay, so it takes this many pounds of force to keep the car on the hill. Okay, so that's how many pounds of force it is required to keep that car from rolling down the hill. The other question was, it wanted to know the force that was perpendicular to the hill. So y'all see that that's what I've called the P. That's the bottom side down there. And so I can do something similar. Here, I'm going to have to use a different trig function. To find P, I want to use something that involves the adjacent side, so I'm going to use cosine. So I'll say here that cosine of 9 degrees is equal to P over the hypotenuse, which is the 5700. And so P would equal 5700 times cosine of 9 degrees. And then that ends up equaling 5,629.82351. And this is also a force, so this will be in pounds. Okay. Once again, let me emphasize that this particular problem I'm working differently than the book does. So if you're trying to do examples like this in your homework, don't click on Help Me Solve This or View an Example. Instead, refer to the example that I've shown you here. This concludes this example of finding required force.